Hello everyone. So we're from group number one, section one of operating system, and today we're going to be demonstrating our animation regarding process coordination. So this topic was split into three different parts, which include semaphore animation, producer consumer problem animation for that, and also um, the Peterson's algorithm. So our team members include NALINI, VIJAYAN, JAYANEYSANRAJ, JAYARAJ, and also me, Herthik, Prathaban. So without further ado, let's first see how the semaphore works in terms of animation and real-world examples.
Semaphore is defined as a non-negative integer variable that is used to solve critical section problems by using two low-standard indivisible operations, which are the wait and signal operations that is used for the process synchronization. Now, let's begin from the scratch of the opening of a restaurant. Once the restaurant is open, the waiter would allow the customers according to the maximum capacity of the restaurant. As we can see, the customers are allowed to enter in the restaurant until the waiter lets in according to the availability of the restaurant. When the maximum capacity is reached full, the other customers are required to wait. And if there is any customers leave from the restaurant, the waiter would receive a signal saying that there is an empty space available for one to dine in. Now, the waiter would give a signal for the first customer in the waiting list to enter in. So, again, the restaurant will be full, and then the other customers have to wait for their next signal to enter inside. So, this is a very simple yet understandable real life implementation that's applied in our surroundings. Thank you very much.
A good day, everyone. Today, I'll be discussing about the producer consumer problem with the small analogy that we came up with. So here we go. So as you can see, a producer consumer problem is basically a bounded buffer problem, which is a classic example of a multi-process synchronization problem. So this problem basically describes two processes, which is the producer and the consumer, which share a common fixed size buffer used as a queue. So the producer will produce a process, whereas the consumer will consume a process. Seems pretty simple, right? But the problem here is to make sure that the producer won't try to add data into the buffer if it's full, and that the consumer won't try to remove the data from an empty buffer. So that's the problem that is faced by a producer and consumer. But some people can find a small misconception in this. So that's why we came up with a small analogy to make you guys understand it better. So this would be the analogy. So the setting would be a factory logistics setting, where the factory will be the producer and the consumer is the warehouse. So in the beginning, at the factory, there'll be a bunch of boxes that need to be transported. So you're gonna need a truck. So in this case, the truck would actually be the buffer or the queue. So when the person calls up and the truck arrives, you fill up the truck or the buffer with the boxes, which is the data, until it's full. Once the truck is full, you cannot add any more boxes in it or data in it. So once the truck is full, you have to transport or consume or remove the data in order to fill it up some more. That's why these boxes are being transported to the warehouse, and the warehouse is the consumer in this case. So now all the boxes are delivered to the consumer, which is the warehouse. So now once all the boxes have been delivered, the truck is now empty again, which means the buffer is empty again. So what it will do is it will go back to the producer and inform you that, okay, the truck is empty, you can put more boxes inside the truck. So in technical terms, it means that the buffer is empty, you can add more data in now, you can produce more data. So yeah, that's what happens when the truck is empty. So that was the analogy. So small recap for the analogy would be the factory is the producer, the truck is the buffer, the boxes are the data that are placed inside the buffer, and last but not least, the warehouse is the consumer. The conclusion from this would be the producer needs to wait if the buffer is full, meaning that once that buffer is full, or the queue is full, or the truck is full, no boxes or data can be pushed inside the buffer because it's full. If it's full, you cannot insert anything inside. Just like how when you just ate and you're full, you cannot eat some more. It's like that. So the producer needs to wait if the buffer is full in order to add more boxes or data inside. And the consumer needs to wait if the buffer is empty. So if you're going to consume something, you need to consume something from a full buffer. So when the buffer is full, you can consume that data. You can consume the data basically. So if let's say the buffer is empty, you cannot do that because there's no data for you to consume. There's no food for you to consume. There's no boxes for you to transfer like that. So yeah, that's basically the whole idea behind the producer consumer problem. And that's all from me.
So hello doctor, so my name is Herthik Prathaban, and so I'm from group number 1 section 1, and today for this demonstration I'm going to be presenting regarding Peterson's solution inside the process coordination subtopic. So I'm sure you've understood like my friend's presentation regarding semaphores and also the producer consumer problems. So with that, now we will be moving on to the Peterson's solution. So first of all, we need to understand what is Peterson's solution. So Peterson's solution, or also Peterson's algorithm, as it's also called that, is kind of like a programming algorithm which emphasizes on the use of mutual exclusion, which allows us two or more processors to share one single resource without any conflicts, where they like have conflicts between sharing memory and communicating between them with a single memory system. So with that, to understand deeply on like how this algorithm works, so we have come up with a real life scenario to explain to you guys how this works. So let's just imagine that we'll see the demonstration video, but the scenario is like this. Let's just imagine that there's a junction, a cross junction, or four-way junction in the middle, and then two cars are approaching this junction, so at a given time. But the thing is, only one car can cross the junction at a given time, obviously, to prevent a crash. So this middle part of the junction is what is our critical section. Now our goal is to uh, prevent any crashes, or allow only one process or car to enter the critical section at a given time. And this is what the Peterson's algorithm attempts to achieve. But in a real life scenario, we use this kind of analogy. So let's just before that, let's just see what is mutual exclusion, because mutual exclusion is a very important factor for this Peterson algorithm. Peterson's algorithm basically achieves to give mutual exclusion to processors, where they can act independently and use and can enter and leave the critical section without any problem. So mutual exclusion is basically part of process synchronization, which says that only no two processes can exist in a critical section at a given point of time, which means at the center of the cross sections only one process or one car can be inside there at a given time. So so this is basically a process synchronization technique, which is also a property of mutual exclusion. So this is mainly used to prevent race conditions or like all the errors. So with that, I think now we can see the demonstration on how this works. So over here we can see that there's a four junction, and currently there's no traffic. I mean, there's a issue and there's no traffic light. The traffic light is not working, so that's why we have a police traffic officer here looking for the traffic. So as you can see, we have two processors, or in this case two cars, coming to the junction. And now when we apply mutual exclusion, the police officer is going to decide which car passes, and he won't let both cars pass at the same time. So first he say he's using the red signal to let the red car pass, so the red car passes, and then he uses the blue signal to let the blue car pass, so the blue car is passing. So if I play that, you can see that it will show the red color, red car passes, and then she will show the blue signal so that the blue car can pass. So that was pretty simple, but there's one issue here. So as you can see, in order for mutual exclusion to work properly, I mean, before we go to the Peterson's solution, actually there are four main conditions for this mutual exclusion to occur properly. So the first two are: no two processes can enter the critical region at the same time, and no assumptions are made about the speed of or number of CPUs, which is what we saw over here. You see that no two processors can enter at the same time. It only allows one of them to enter, and we don't know how many processors or cars are going to enter, so we just mutually exclude them. So those two, rule number one and rule number two, are satisfied here. But how about rule number three? So rule number three is called starvation. So I'm sure you've heard of it before. Starvation is where no process outside the critical region may affect or block the process from entering the another process from entering the critical region, which means that once a process exits the critical region, in this case the red car has already exited the critical region, which is in the middle, this part, it has exited the critical region, but it is, as you can see, it is actually spending too much time in the non-critical region. So because of that, because it's spending so much time in the non-critical region, the blue car, because the signal, the turn is now the red car's turn, but it's not even finished the round yet. So the blue car over here has to wait for this uh, car to finish its job in the non-critical region, then only this car can go. So it's waiting for a long time, and this is what we call starvation. And according to the conditions of mutual exclusion, starvation cannot occur. We should actually prevent starvation. So how we solve that is by introducing traffic signals. So as you could see, we have traffic signals here. So we have two triggers. So when both traffic lights are green now, so when this blue car enters, it has two triggers. So when this blue car enters the critical region, it turns the signal red. So no car from the other direction or no processes can enter the critical region. So you see, as we move, the red car comes in and it stops. You can see that it stops because there's a red traffic light. It cannot enter the critical region, so it stops. But you can see that's the blue trigger here. So when this car stops, it actually triggers the other traffic light, red. So you can see that from green color, when the car triggers the blue signal, it turns to red. So which means that no more blue process can enter the critical region also. So whatever is inside the critical region, it's fine, but no more cars or processes can enter the critical region because this car is already waiting. So as you can see, so it's waiting, turn the red color. Now when the blue car leaves the critical region, it turns back the signal to green, which means it's saying that I'm done. Whoever wants to enter can enter now. So the red car sees this signal and it's gonna go inside the critical region. You can see that it goes inside critical region, and when the red car also, when it's done with the critical region, when it moves out of the critical region, it is gonna turn the red color signal to green, the opposite signal to green, saying that it has finished its job in the critical region. Now the blue car or any other process can enter the critical region because the critical region is free. So this is how we prevent starvation, which is the third rule. Okay, now everything seems good, right? Everything is solved, but there's still one more rule we have to check out, which is the deadlock situation. So a deadlock situation is basically where two processes should not endlessly wait for any message that will never arrive, which means they are both stuck in a a loop where they don't get any message, they just wait forever and ever. So that's the deadlock situation. So how we can, so this so over here we're going to see how the Peterson solutions work. because it solves all of these problems. That's the Peterson algorithm. So so let's just demonstrate. Let's see both cars. In this case, you can see that no one is in the critical region, so both traffic lights are green. So but both this red car and blue car are going to be coming at the same time, every exact second, exact millisecond. So they're going to enter this trigger, blue and red trigger, at the same time. So you could see that they enter the same time, and both traffic lights are turned to red. Before this, only one was red, one was green. So one car can enter the critical region, but because both of these triggers entered at the same time, both traffic lights are red, so both cars cannot enter the critical region now. So this is a problem because they are in a technically they are in a deadlock where they are not going to receive because the blue car is going to wait for this signal to turn green, and the red car is going to wait for this signal to turn green. Then only they can enter. But both of them don't know that there's no process in the critical region, and they're going to be stuck in a deadlock. So to solve this, we introduce back our police officer. So this acts as an extra layer of security, or maybe taking turns in the algorithm, so like the second priority, while using an AND gate. So what will happen is that in the event that both of these traffic lights are red, which means no car can enter, so these cars will be managed by the police officer's signal. So you can see that the police officer sees the red car first, let's just say, so that he's going to allow the red cars to enter. So the red car is going to enter the critical region, and once any of the car enters the critical region, the process is fixed, because once one of these cars enter, it is going to do its critical region job, and when it exits the region, it's going to turn the signal to green. So now we have a normal situation where one of the traffic light is green, one of it is red, so the process can continue smoothly. So as you can see, the blue car enters, it turns back to green, and the process continues smoothly. So that is our mutual exclusion, how Peterson's solution solved the mutual exclusion, uses the mutual exclusion concept to solve this problem. So that's all from us. I hope you like this video animation. So thanks for watching.